This video is to explain about Kruskals algorithm, Prim's algorithm and Dijkstra algorithm. Kruskals algorithm is a minimum spanning tree algorithm that finds a subset of edges that connects all vertices in a weighted graph with the minimum total edge weight. It uses the disjoint set data structure, which efficiently uses union and find to detect cycles and ensure that no cycles are formed while constructing the minimum spanning tree. Here are the algorithm steps to find the minimum spanning tree. First, we sort all the edges in increasing order of their weight and initialize a disjoint set for each vertex. Iterate through sorted edges. If the edges does not form a cycle, then it belongs to the minimum spanning tree. Union the set of the two vertices. Repeat until a minimum spanning tree has v minus 1 edges for a graph with v vertices. Let's know about disjoint set operations. Disjoint set operation contains three operations: make set, find set and union. Make set creates a new set containing only the vertex v. Each vertex is its own parent initially. And find set finds the representative of the set containing v. Union merges the set of u and v using union by rank to keep the tree balanced. Let's consider an example graph and we apply the kruskals algorithm to obtain minimum spanning tree. Firstly, we sort the edges according to the ascending order of the weight. Here is the order. And next, initialize the disjoint sets. That is, each node start as its own parent. That is called self set. And process each edge using union and find operations. For edge AB, the weight would be 1 and the find set or union set are given by the following. So as it does not form a cycle, we update the MST with the edge AB. And we repeat the process with edge DE and edge BC and edge CD. As we got all the edges, all the vertices in our MST, we stop the process. Now our minimum spanning tree will look like this. And the cost of the minimum spanning tree would be 10. The time complexity of Kruskals algorithm would be O of E log E and the space complexity would be O of E plus E. Here are the Python code and the output of the Kruskals algorithm. Let's move on to Prim's algorithm. Prim's algorithm finds the minimum spanning tree by growing a single tree. It always expands the minimum spanning tree by choosing the minimum weight edge, connecting a vertex inside the minimum spanning tree to a vertex outside. The data structure used are binary min heap and hash map. Binary min heap is the priority queue which efficiently retrieves the smallest weight edge, and hash map would maintain the mapping of vertices to edges. Here are the algorithm steps to obtain a minimum spanning tree using Prim's algorithm. First, pick any vertex as the starting node, create a min heap, use a hash map to track the minimum edge and mark all vertices as not included in the MST. Then insert initial edges into the heap. Then iterate until MST contains v minus 1 edges where v would be the vertices. Repeat it until all vertices are included. Return the MST and its cost. Let's consider the same graph which we have taken for the Kruskals algorithm and apply Prim's algorithm to the graph. Then we process each edge by updating its heap and also vertex edge map. We also update the MST while processing each edge. We'll continue till we have all the vertices in our MST. Then the minimum spanning tree would look like same from the Kruskals algorithm. And the total minimum cost would be same, which is 10. The time complexity of Prim's algorithm would be O of E log V and space complexity would be O of V plus E. This is the Python code and the output. Now we move on to Dijkstra algorithm. It finds the shortest path from a source vertex to all other vertices in a graph with non-negative edge weights. It uses a binary heap for efficiently retrieving the vertex with the smallest distance and hash map to store distance and parent relationships. The algorithm follows as we initialize data structures, which is vertex distance and vertex parent. And also, while the heap is not empty, extract the vertex u with the smallest distance from heap. For each neighbor, we follow this formula to compute the new distance. If the new distance is smaller than the vertex distance, update vertex parents. And when the heap is empty, return vertex distance and vertex parents map. We consider the same graph as the above, and we follow the Dijkstra's algorithm to obtain the shortest distance from the root node A to every other vertex in the graph. Now the final shortest path of the graph is given by A to B is 1 and A to C is 4 and A to E is 5 and A to D is 7. The time complexity would be O of V plus C log V and space complexity would be O of V plus C. Now we'll see the Python implementation of the three algorithms. Firstly, the kruskals algorithm. We have declared a class of disjoint set and we have declared several functions to find and union set operations. And then we have given the vertices and the graph edge cost. Then we'll see the output. So the output is like this. We got our minimum spanning tree. Next we move on to Prim's algorithm. This is the Prim's algorithm in Python code. We have taken the same graph as our example. Then we'll run this code to obtain minimum spanning tree. This is our minimum spanning tree. Nextly, we move on to Dijkstra's algorithm. This would be the Python code, and we have considered the same graph.